So in the last class, we had derived the principle of virtual work, and we also said why the word virtual, right? Let me just write that down. So it was integration over the Newman boundary of the applied traction dot with virtual displacement eta ds naught plus integration over the volume v naught rho naught b dot eta dv naught, and that's equal to the first p वाला लिखो p double contraction gradient of eta dv naught. Okay, so this is the principle of virtual work pvw. The terms on the left hand side, it's also called del w external because it's a virtual work due to external loads, whereas on the right hand side that's del w internal. Okay, so pvw just says at equilibrium the virtual work done by the external load will be same as that by the internal stresses. Okay, so this is also a equation in its own, so you don't have to start with the strong form, although we derived it from a strong form, but you can now directly start from here and solve for the equilibrium, and the entire finite element method is based on the principle of virtual work. All right, any query on this topic? I'm going to then move to the next topic if you don't have any query. Okay, so another way to obtain equilibrium equation or equilibrium configuration is through minimizing the total energy of a system. So you all must have learned in your mechanics course that any system minimizes its energy, and at equilibrium it attains the minimum energy, right? So here also, so we learned that in the context of particles or for rigid bodies, but now we want to do it for deformable bodies. Okay, so this is another principle of minimum potential energy. Minimum potential energy. So that's the next topic now. Can you guys hear me?
Yes, sir.
Okay. So we have to obviously first write down the expression of potential energy of the system. So our system is the deformable body which is subjected to external loads, right? So this is your T naught, and then you can also have body force throughout the body, which is B naught. So we have to first write down the expression of potential of the system. Now the potential of the system, let us say I denote it by I, which is going to depend on the unknown small f, which is itself a function. So this potential will be equal to the stored energy of the system or the strain energy of the system, for which you have to integrate over the volume. Okay, so this is the total mechanical energy for elastic problem. we can say mechanical stored energy, and it's also called internal because it's in the body. And then we have to subtract the work done by the external loads. Okay, work done by external load has to be subtracted to get the total potential of the system. So on the left hand side is the total potential of the system, which has to be minimized. So in this, we have internal energy of the system minus the work done by external load. You might be thinking, why do we have a minus sign? So it's because, if you think of whoever is applying the load as also being the part of the system, then as the agent who is applying the load, it does some work on the deformable body, the energy of the agent will decrease, right? Because it is doing some work on the deformable body. So for the system of the body and the external agent as a whole, the gain in the energy of the deformable body is just the first term here, and the second one is the change in energy of the agent, and it has to come with a minus sign because the agent is doing a positive work on the system, so its own energy reduces. So in a way, the total is the energy of the closed system, which is the body itself plus the external agent. Okay, so this explains why we have a minus sign here. The body itself is not an isolated system, no, because it is working, it is in contact with the external agent. If the body were an isolated system, then this second term was not required. Okay, so anyway, so now we have to write down the expression of the work done by external load, and the external load here is your B naught and T naught. Now here comes the difficulty. To get the work done, assume that this is a reference configuration. So this is the reference configuration, and maybe it deforms like this, and that's a deformed configuration. So as the body undergoes this deformation, we figured out last time that this T naught and B naught can also change, isn't it? As the body undergoes deformation, T naught and B naught can change during the deformation process. So how do we write down the expression of work done? So to know the expression of work done, then we have to know what is the path followed by each of the point in the body. Which path did the point follow? And you have to then integrate over that path to get the total work done, isn't it? But whenever you solve a deformation problem, you don't really know what is the path followed by the deformation. So therefore, it is difficult to write down the work done by external loads here. So difficult to write down, or we cannot write. We cannot write usually because we do not know the path of deformation. Path of every material particle of the body during deformation. Okay, but there are conservative loads for which the work done only depends on the final position and initial position, isn't it? You must have learned about this. There are two kinds of load: conservative load and non-conservative load. So luckily for conservative loads, we don't need to know the path of deformation because the work done is independent of the path. So for such loads, we will be able to write down the expression of work done by external loads. Okay. So you see, to apply this principle of minimum potential energy, it is important that we be able to write down the expression of the potential, which consists of the internal energy, which is the strain energy, minus the work done by external load. Yeah, somebody has a question?
Yes, sir. So we know that the gravity force is usually a conservative force, but how can we externally apply a conservative load?
I mean, just like gravity is acting, it's a conservative force, isn't it?
Yes, sir.
Similarly, if you have, if you apply a constant force, for example, then it's also a conservative load. Because for a constant force, the work done is simply F dot final position minus initial position. It does not depend on the actual path taken. Because when you do that integration, F dot dr over the path, F is constant, it comes out of the integration. So you just have F dot integration of dr, which is simply F dot final position minus initial position,
Okay, sir.
right? So constant force is one of such examples which comes under conservative load. And then, for example, spring force. So if you attach a spring to this body, think of attaching a spring, then the work done by a spring is also conservative because you can always express the work done in terms of the potential energy of the spring, isn't it? Half kx square, half kx square, where x is the total change in length of the spring. So it does not depend on what path was taken by this point during deformation. It just depends on the initial point and the final point. If you know initial and final, you can find out using trigonometry the change in length of the spring. And that is all you need to obtain the work done by the spring, right?
The path taken by point A and point B are the deformation map.
Yes, they are the deformation map during the deformation process.
Yeah, then we can find that deformation map as we have discussed, like using LMB and the constitutive relation.
When you are doing, so if you are, of course, if you are doing dynamics, then you can find the deformation map.
Yes,
For statics, when the question is you are applying a load and you want to know what is the final configuration, so there it is irrelevant to find out the path of deformation, right? Of course, if
yes,
you
sir.
have in the actual physical scenario, a body will reach from undeformed to deformed configuration through dynamics, through an actual path. And that path you can know by solving the dynamics equation. And once you get that path, then you can get the work done by all kinds of forces, whether it is conservative or non-conservative, because you know the path. But you have to know the path in that case, right? Here, when I'm formulating the principle of minimum potential energy, I want to formulate the right hand side just in terms of the small f, that is the deformed, which maps undeformed to deformed. So this small f is only from undeformed to deformed for the case of statics. So this does not know what is the actual path taken. That is not present here. Okay, so we are doing it for statics, and this f maps from undeformed to deformed. Actual path taken is not in the picture here. I mean, at least in f. The f that we have here that we want to solve for. See, in statics, we just want to know if you have applied some load to a body, what is the final deformed shape of the body. So this is what the problem is here. So for such a problem, you don't know the actual path taken, so you cannot write down the work done. And also suppose that somehow you find out the actual path taken, and then you can obviously compute the work done. But then there is nothing to solve for because you have already found the path and you already know what is the undeformed and what is the deformed configuration. So then there is nothing to solve, no? Here our goal is to solve for the deformed configuration. अगर तुम्हें पाथ पता चल ही चुका है तब तो तुम्हें डिफॉर्म कॉन्फ़िगरेशन भी पता चल चुका है, तो फिर ये सब करने का तो जरूरत ही नहीं है. So you have to understand what problem we are solving. What we are solving is we are given the undeformed configuration and we are told that okay, this is a load that you are applying. So we have to find out what is the deformed configuration. That is the problem, and which we want to solve through this principle of minimum potential energy. Okay.
Sir, one more thing. I wanted to know that
Hmm.
जो हम लोग पोटेंशियल एनर्जी पढ़ते हैं मैकेनिक्स में पढ़े थे वो इन जनरल ग्रेविटेशनल पोटेंशियल एनर्जी होता है.
हाँ.
यहाँ पे जो आपने बोला कि टोटल पोटेंशियल ऑफ द फंक्शन, तो यहाँ पे पोटेंशियल का को कैसे समझे कि ये पोटेंशियल क्या है?
Yeah. So I was just telling you now. Just a second. So for conservative load, I'm writing that a potential function of work done exists, basically, and this potential function is in terms of current configuration. You don't need to know the path, not in terms of actual path of deformation. Yeah, so what he's saying that in mechanics, suppose you have a body which is acting under gravity and you also may be having springs attached to it, then you can visualize that okay, you have the potential, gravitational potential and the spring potential, which together has to be minimized, right? So you are minimizing that potential. So what is it that you are minimizing here? So as you can see, the first term is the strain energy of the body itself, but you are not minimizing the strain energy of the body, क्योंकि अगर वो रहता तब तो हर केस में वो तुम्हें रेफरेंस कॉन्फ़िगरेशन मिल जाता, राइट? क्योंकि रेफरेंस कॉन्फ़िगरेशन में एनर्जी जीरो होता है. तो फॉर एवरी, अगर तुम ये सोचते कि अच्छा अगर वी जस्ट हैव टू मिनिमाइज द स्ट्रेन एनर्जी, तो फॉर एवरी प्रॉब्लम यू वुड गेट द रेफरेंस कॉन्फ़िगरेशन, बट यू नो दैट इज नॉट द केस. So you have to also have this extra term, which is minus the work done by external load. And what is this extra term? This is exactly the potential of the एक्सटर्नल एजेंट, जैसे अगर स्प्रिंग रहता तो वहां यहाँ पर वो जो माइनस वर्क डन बाय स्प्रिंग इज इक्वल टू पोटेंशियल ऑफ द स्प्रिंग, and spring and the body are acting together, they are acting on each other. So as a whole it is then the potential of the body plus spring. So basically on the right hand side it is the potential of the body plus the external agent which is in contact with the body or which is influencing the body. Okay.
हाँ सर, सो बेसिकली ये जो जो भी इन्फ्लुएंस कर रहा है, ये वर्क कर रहा है बॉडी पे, उसका जो कैपेसिटी है उसको पोटेंशियल बोल रहे हैं।
yes exactly.
ओके सर।
Okay, so you see all this discussion brings us to the or highlights us the limitation of this method, that is the principle of minimum potential energy. So it says that we can apply this only when the load that is acting on the body is conservative. क्योंकि अगर कंजर्वेटिव नहीं है तो हम उसका वर्क डन नहीं लिख सकते हैं in terms of the current configuration, and therefore हमारे पास एक्सप्रेशन ही नहीं रहेगा जिसको मिनिमाइज करना हो, right? So this is the limitation. Principle of minimum potential energy, MPE, can be applied only when all the external loads acting on the body are conservative in nature. Okay, and one example is obviously the constant loads, but there are of course many more examples. For example, the spring force. Spring force is not a constant force, right? It depends on the change in length of the spring, but you can still write down its potential. So one example here is constant force. And you must have learned in your mechanics that if you know the force field, if force field F is known, so the criteria for conservative field is the following criteria for conservative force field. So you can check it through following criteria. So F is the conservative force field, then its curl must vanish. If this is equal to 0, that means it's a conservative force field. Okay, so anyway, so with this in mind, let us restrict ourselves. Let us talk about constant forces. Let us talk about, but understand that we can do it also for conservative forces in general. So let us talk about constant traction T naught. So it is just a function of big X, but not a function of small f. It does not depend on the configuration of the body. And see, constant meaning it is independent of the configuration. It can vary as a function of big X, but it is independent of the configuration. So I'll make it more clear here. So this constant it means it is independent of the configuration. For example, the spring force, it depends on the configuration. जैसे बॉडी जितना डिफॉर्म करके जहां भी होगा उसके हिसाब से निकालेंगे कि कितना उसका कंप्रेशन या एलोंगेशन है स्प्रिंग का, और फिर उसका फोर्स निकलेगा. So force, spring force depends on the configuration, but still it is a conservative force. Here we are talking about constant loads which are independent of the configuration. So for such loads, what will be the work done? So work done by T naught of big X. So you have this body and T naught of big X is acting. Think of a point A here, which goes from big X A to small x a. Okay, so the work done will be in going from big X a to small x a. T naught of big X a dot with dr, isn't it? And then this T naught may be acting over a small area, ds naught. And to get the work done by all the traction field, you have to have another integration over the Newman surface. Okay, and you see this thing over here, because T naught is independent of configuration of the body. So as the body deforms from big X a to small x a, the traction T naught at a is not changing. That's what I mean when I say it is constant. So it can come out of the integration and it becomes S naught n T naught of x a dot, and ds naught is also here obviously, dot with dra in going from big X a to small x a. Okay, which finally you can write S naught n T naught of big X. If you generalize this big A to being any point on the surface, then big X A is simply big X dot with small x minus big X, right? ds naught. So that's the work done by this T naught. Which you can also write as T naught of big X dot with small f of big X minus big X ds naught, isn't it? Similarly, work done by b naught of x. So using similar logic, it's going to become integration over the total volume V naught, and you have rho naught B naught big X dot with small f of big X minus big X dV naught, isn't it? Are you all comfortable with this? So having found the potential, then the total potential of the system I F that's equal to internal potential, which is the strain energy, W big F dV naught minus over the Newman surface T naught of X dot with F ds naught minus okay, I have done this B naught here, it's just B, and then you have, you see, you have those extra terms also, plus S naught N T naught of capital X dot with capital X ds naught right. But interestingly, these last two terms, it's a constant. So it is independent of the configuration. So when you minimize this potential energy by changing this small f, the configuration, which you have to find out, right? So you have to find out for what configuration this potential is going to be minimized. So for that, you will change the configuration and find out for which this is minimum. So when you do that, this green box, it acts as a constant, right? It is independent of configuration. This does not change. So it is like a constant energy, and therefore this can be dropped from the total potential because it's a constant energy. It does not lead to anything when you do the minimization. Okay. So the remaining thing is the potential which has to be minimized. So how do we do the minimization? You see, first of all, the left hand side, the way it is written, it's a function of function. So therefore it's also called functional. I is a function which depends on a small f, which is also a function. And you know, this is at the heart of solid mechanics. There are many problems which you can solve through this energy approach, where you start with energy and minimize to get the equilibrium equation. See, we have started with the principle of minimum potential energy. So we don't know what will be the equilibrium equation or what we will get when we minimize this. So let us see what do we get after minimizing this. Okay. So how to minimize this? So you have to minimize with respect to function. We have learned how to minimize with respect to variables. But here we have to minimize with respect to function. So that is not an easy thing. So, but what we can do is, suppose that F epsilon is equal to F equilibrium, the actual unknown F equilibrium, plus epsilon into eta. Here eta is also a function of big X. So this eta is something through which you are perturbing the configuration. So you are checking for different configuration. As you change eta and change epsilon, the total configuration F epsilon is changing. And then you can see among them which is the minimum. But the most important thing that is happening here, through this technique, you are able to mathematically write down the change in function f in terms of this scalar epsilon. Of course, eta is also there, but you have also this scalar epsilon, which you can change to change the function. So you can now think of minimizing with respect to epsilon. When you think of minimizing the energy functional with respect to function through this approach, you can now think of minimizing this with respect to scalar epsilon. And this is something you know how to minimize with respect to scalar epsilon. You just have to set the derivative of the function with respect to epsilon equal to 0, isn't it? So let us write down first I f epsilon. So wherever you have f, you have small f, that has to become f epsilon. So first is the strain energy. So it is W of big F. So big F will become big F epsilon minus S naught N. And you see this big T naught is independent of a small f, so it remains big T naught. This does not change because it is independent of epsilon. Dot F epsilon ds naught minus V naught rho naught B, and B is also independent of configuration, so this will not change when you perturb this. Dot F epsilon dV naught. So this is the epsilon energy, and we have to minimize this. So all that you have to do is di epsilon by d epsilon and evaluate it at epsilon equal to 0. And this should be equal to 0, right? If Fe, if this is the equilibrium F, so that means when you evaluate this derivative at epsilon equal to 0, because at epsilon equal to 0 you get F epsilon equal to Fe, and at that configuration the energy has to be minimum. So therefore this derivative must be equal to 0, right? Now let us work it out. What are we getting? So from the first term you have dw by d epsilon, right? Now you can use chain rule, and this becomes del w over del f double contraction df epsilon by d epsilon, and evaluated at epsilon equal to 0 into dv naught minus the next term. You have T naught of big X dot with df epsilon by d epsilon at epsilon equal to 0. Then the last term, okay, and this is equal to 0, this whole thing. So finally this becomes del W by del F double contraction. You see, what is this going to become? We have also worked it out in the last class. This is simply gradient eta, isn't it? Just look here. When you take the gradient, you have gradient F epsilon equal to gradient Fe plus epsilon into gradient eta. And when you do d by d epsilon, this will act like a constant, and so you just get the second term. Okay, so you have gradient eta minus T naught dot eta. See, d small f by d epsilon is simply eta minus dot eta. Okay,
सर
या
पहली टर्म में डेल डब्ल्यू अपन डेल एफ एप्सिलॉन क्यों नहीं लिखा, सिर्फ डेल एफ ही लिखा, चेन रूल लगाया तो?
हाँ देखो, ये वही चीज आ गई कि हमें we are just thinking that W is just a function of big F, but उसको F equal to F epsilon पे evaluate करना है. W is always a function of big F. It's just that it has to be evaluated at F equal to F epsilon. So I can, यहाँ पर इसको थोड़ा different तरीके से लिखते हैं. W at big F equal to big F epsilon.
ओके सर.
Okay, so and here for example, when you set epsilon equal to 0, this is del W of del F, but evaluated at F equal to big F E at the equilibrium. All right, because when you set epsilon equal to 0, big F epsilon becomes equal to big F E, right? You just look here. So on the left hand side, it is big F epsilon. This is equal to big F E plus epsilon times grad eta. And when you set epsilon equal to 0, the second term goes away. Anyway, so we come back here. So, we now want to use localization. So, what we are doing right now is called calculus of variations. So we are varying the function. And what we want to do is somehow express the first term in terms of eta. So we have to move the derivative from eta onto the first term. Okay, remember in the principle of virtual work we did the opposite. Now we are going to move the derivative from eta to the first one. So let us think of using index notation. So this one we can write as, and we know del W del F is P, isn't it? So it is Pij into del eta I over del xj, isn't it? Which is same as integration over V naught del over del xj of Pij eta I dV naught, which is equal to sorry, there's also one more term is going to be there, so you have to subtract yeah, del Pij over del xj eta I, isn't it? Now you can think of using, going back to tensor form, and you see what is this. This is divergence dot P transpose eta. If you work it out, this will be divergence dot P transpose eta. Okay, whereas this first term here, this is divergence dot P dot with eta. You can prove it using index notation. Just work it out, expand it, and you will see that this is what it is. Okay, so now the first term, it is divergence of some vector. You can apply Gauss divergence theorem, right? And it becomes over the surface S naught P transpose eta dot with the outward normal big N ds naught minus divergence dot P dot with eta. Okay. And also one thing that I forgot to say, this eta that you have here. So, you have to, when I said you have to minimize this energy functional with respect to configuration, so you have to look for different configuration and see for which configuration is the minimum. So when you search for those functions of configuration, those functions must be all compatible with the any boundary condition that you may have prescribed. For example, if the body is clamped on some part of the boundary, then when you change this, change the function through epsilon and eta, then because Fe, the equilibrium F, it must be satisfying that boundary condition, this eta must vanish on those boundary. So that's the admissibility, just like we were doing in principle of virtual work. So this eta, it has to be admissible. So we have to search for minimizing this potential energy only over the admissible perturbations. So let us now come back to our derivation and substitute it here and see what we get. So we have integration over S naught of P big N dot with eta. You see, I brought this P transpose on the other side. ds naught minus divergence dot P dot with eta minus S naught N of T naught dot with eta ds naught and the last term, and this has to be equal to 0. And now you see in the first term here, eta has to vanish over the Dirichlet surface, isn't it? Because there the body is clamped. So you can also write this just over the Dirichlet surface. Sorry, just over the Newman surface, S naught N, P N. But then you see, you can also combine these two and you have Pn minus T naught dot with eta ds naught, and then the remaining one you combine minus integration over volume V naught, so basically these two, divergence dot P plus rho naught B dot with eta dV naught equal to 0. Okay, now you see it's very interesting what you have gotten now. So this term here is over the volume and this is over the surface. And because your eta can be arbitrary, right? Eta can be arbitrary, it just has to be admissible. So that means each of the integrands must vanish. So from here, you derive the equation of motion or the governing equation along with the boundary condition also for all x. So here it is for all x in V naught, and the boundary condition is that P big N is equal to T naught for all x in that Newman surface. So can you see, you just got back the equilibrium equation. Earlier you had derived using Newton's second law, linear momentum balance, but now you derive the same thing using principle of minimum potential energy. So what you have derived is that if you let a system minimize its potential, the governing equation is the same that you obtain from the linear momentum balance. It's just that the derivation using minimization of potential energy is restrictive in the sense that the external loads must be conservative. Otherwise, you get the same equation. Okay. Likewise, also you see the principle of virtual work that we worked out in the last class. This is also general. You recall there is no restriction that your body force or the surface traction T naught be conservative. You remember we said that it's virtual because we are just freezing the T naught and B naught, B. But in reality, it could change as the body is deforming. You remember? But because we are not allowing that change, therefore it's a virtual work. So in virtual work theorem, the body force and your traction T naught can be arbitrary. So this is more general. So in that sense, PVW is more general than principle of minimum potential energy. Okay, so we can make that remark now. Okay, any query on this?
This is valid only for dead load, means T naught and B will be the dead load here, or they can be live loads, sir.
So this minimum potential energy is valid for conservative loads for which you can express the potential. Dead load is one example of conservative load, but otherwise it is valid for any conservative load. Any more question? No question? Okay, and as I told you, this principle of minimum potential energy, although it is restrictive, but this is extremely useful in solid mechanics. Why? Because you see the linear momentum balance equation. To get that, to obtain the equation, it is easy when you have just elasticity going on. Think of a problem in which you have multiphysics. That means you have mechanical deformation, you have chemical reaction, you have magnetic interaction, you have electric interaction, you have all of them together. तो उस केस में हमारा इक्वेशन क्या होगा ये कैसे जानेंगे? हम लोग किस इक्वेशन को सॉल्व करेंगे जिससे कि प्रॉब्लम सॉल्व हो जाए? But there this potential energy concept comes as a handy. What you can do is you start with writing the energy. Writing the energy is always easy because it's first of all it's just a scalar और तुम्हें पता रहता है कि हर डोमेन का इलेक्ट्रिक पार्ट का एनर्जी क्या होगा, मैग्नेटिक पार्ट का एनर्जी क्या होगा, एनर्जी का एक्सप्रेशन पता रहता है. So you can write down the total energy involving mechanical energy, electric energy, magnetic energy, chemical energy, and subtract with the external loads the potential of external load and minimize it. And then as a process of that minimization, you will get the governing equations. So equations will come out automatically through that process of minimization. And obviously they will not be what you would have seen before. So this concept is very well used in problems where you don't know what will equation be looking like. And the step is quite straightforward. You just have to write down the expression of total potential और उसको minimize करना है with respect to all the relevant unknowns. In this case, where you have just a mechanical problem, the unknown was just a small f. Okay, and suppose if you are working with electroelastic problem, there is a theory of electroelasticity. Where you have a body which is acting under some applied electric field, and if the body is electrically active, then due to application of electric field, the body can also deform. So here electric and elastic fields are coupled. Okay, or you could also say electric and elastic energy are coupled. So what are the unknowns here? The unknown here for the mechanical part is that same small f, and for the electric part it is the electric potential which is the unknown, and that's a scalar quantity, electric potential, scalar electric potential. So how do we get the governing equation to solve for small f as well as phi? So it is very straightforward. All that you have to do is you have to start with the energy involving both the mechanical as well as electric energy, and you just minimize it with respect to the unknowns, both small f and phi. And as a process of that minimization, you will also obtain the equations, the governing equations. Okay. Having said this, I should also put a disclaimer. Often, not often, but many a time you get garbage equations. The equations that you obtain as a process of this minimization, many a time you get garbage equations. So it always has to check through physics whether those equations are making some sense or not. Okay. Well, again, not often, but sometimes it happens. But generally, you get correct equations. Okay. Yes.
So, sir, the equation that we got the equilibrium equation, but when we were deriving the equilibrium equation, we did not assume the body force to be conservative, and similarly for the traction equation also.
Right.
But
so therefore,
we were able,
those approaches are therefore the principle of minimum potential energy is restrictive in the sense that you can do it only when the body force and the tractions are conservative.
so we were able to derive these equations only because we were able to because we considered the forces to be conservative.
Yeah.
Otherwise, we couldn't have derived it.
Yes. Correct. If you want to use minimum potential energy, the forces have to be conservative. तभी ये निकल सकता है, क्योंकि तुम्हें स्टार्ट ही करना है with the expression of potential which has to be minimized. So पोटेंशियल का एक्सप्रेशन कब आ सकता है? तभी लिख सकते हैं जब वो फोर्स कंजर्वेटिव हो. फोर्स कंजर्वेटिव नहीं है तो हम लोग पोटेंशियल का एक्सप्रेशन ही नहीं लिख पाएंगे, राइट? दिस एक्सप्रेशन हम लोग यहाँ लिख ही नहीं पाएंगे, तो क्या मिनिमाइज करेंगे फिर?
So then for any forces that we have in our system, पहले we will have to satisfy that criteria of conservativeness.
Yes.
And फिर उसके बाद we will proceed.
Yes, yes. That is true. Say again.
And in this equation also, which we have written here,
yeah,
internal total energy, mechanical stored energy will 0, then we get the same equation which we use in the general mechanics. Then, sir, why this negative sign is, I mean, there and here also it's coming? I think you explained, but I'm not getting that.
Okay, let me explain it again. Why this negative term? This is always, many faculties also would not know this negative term. Basically, देखो अगर एक जनरल मैकेनिक्स सोचो, जब स्कूल में पढ़ते थे तो हम लोग क्या करते थे कि कोई भी सिस्टम इक्विलिब्रियम में अपने एनर्जी को मिनिमाइज करता है, राइट? ये हम एक जनरल सोचते पढ़ा है हम लोगों ने कि एनर्जी जो है सिस्टम का मिनिमाइज होता है इक्विलिब्रियम में, बट दिस इज एप्लीकेबल ओनली फॉर अ सिस्टम विच इज इन आइसोलेशन। कोई अगर आइसोलेटेड सिस्टम है तो उसका इक्विलिब्रियम उस सिस्टम की एनर्जी को मिनिमाइज कर दो, उससे मिल जाएगा। But in mechanical deformation problems, for example, you have this body. It is not an isolated body. It is under the influence of external loads. ये अकेले एग्जिस्ट नहीं कर रहा है, राइट? इस पे बाकी एजेंट्स भी फोर्सेस लगा रहे हैं जिसके कारण ये डिफॉर्म कर रहा है। अगर ये आइसोलेशन में रहता, दैट मीन्स इसमें कुछ फोर्स नहीं लग रहा होता, तब तो फिर इसका एनर्जी जो है बस इसका जो इसके अंदर जो भी एनर्जी स्टोर हो रहा है वही है, और फिर उसको जब मिनिमाइज करते तो तुम्हें इसका स्ट्रेस फ्री कॉन्फ़िगरेशन मिल जाता। बट बिकॉज इट इज not isolated and it is in contact or it is being influenced through external agents, so therefore you have to think of a system जो कि isolated हो। सबसे पहला वो सिस्टम होगा this body plus that external agent, right? Then you can apply the principle that for that system the total energy has to be minimized, but that system has got body whose energy is the first term here, and then the external agents whose potential energy will be negative of the work done by those external agents, क्योंकि external agents whatever work they do on the body, they are going to lose that energy, right? Their energy will reduce. If they do some work on something else, their own energy will reduce, so therefore their potential comes with a minus sign here. जितना भी उन्होंने वर्क किया उसका माइनस करना पड़ेगा टू गेट व्हाट इज द चेंज इन द पोटेंशियल ऑफ एक्सटर्नल एजेंट, ओके? एंड देन एज ए होल it is the energy of that isolated system which consists of the body plus the external agent, and then you can think of minimizing the energy of this isolated system. Okay, is that understood?
Yes, sir. So, sir, basically हमें आइसोलेशन के बारे में सोचना है कि the system should be in isolation. The
Exactly.
body and the external agent also, both are the system.
राइट। अब ये ऐसा सोच सकते हो कि व्हाट इफ एक्सटर्नल एजेंट भी किसी तीसरे बॉडी से कांटेक्ट में है? ऐसा भी होता है कि जो भी बॉडी पे फोर्स लगा रहा है वो खुद भी किसी और से इन्फ्लुएंस हो रहा हो, तो फिर उसको भी सिस्टम के अंदर लेना पड़ेगा।
Okay.
Yeah. For example, think of moon and earth. So मून एंड अर्थ के बीच में ग्रेविटेशनल पोटेंशियल लगता है, तो अगर बाकी प्लैनेट्स, अगर सिर्फ मून का सोचे हम लोग कि मून का कॉन्फ़िगरेशन क्या होगा, कहाँ पे उसका इक्विलिब्रियम पोजीशन होगा, देन मून इज बीइंग एक्टेड अपॉन बाय अर्थ, so therefore we have to think of moon and earth together as a isolated system. but suppose कोई एक तीसरा प्लैनेट भी है जैसे मरकरी या मार्स जो कि काफी क्लोज है अर्थ से, and if it is also influencing the earth, तो फिर हमें मून, अर्थ और मार्स तीनों को मिलाकर एनर्जी को मिनिमाइज करना पड़ेगा, so that you finally have an isolated system to work with. Okay.
Yes, sir.
In the next class, we'll learn about what is called stiffness tensor or elasticity tensor. That is the second derivative of this W with respect to big F. First derivative is your Euler-Kirchhoff stress, and second derivative is called elasticity tensor, which when evaluated at big F equal to identity, that means in the reference state, that gives you that CIJKL जो हम लोगों ने linear elasticity में पढ़ा है. Okay, so we'll learn something about that stiffness tensor or elasticity tensor in the next class.